So in this question we've got a lighthouse and there are two ships. The lighthouse is at the origin and there is a ship at -4i plus 3j. So that is -4i plus 3j, about here, roughly-ish. And that vector there describing where that ship is, that is -4i plus 3j. And he's there. And his velocity is 4i plus 17j. So he's going 4i plus 17j is going quite steeply in that direction. This is his velocity vector. So every hour, that's what he's going to do. 4i plus 17j. So he'll go, in the first hour he'll be here, second hour he'll be here, third hour he's gone off the page. Okay, our other ship, he is at, where is he? 4i plus 9j. So 4i plus 9j, he's starting off there. 4i plus 9j. Now his velocity vector is -12i plus 5j. So every hour he goes -12i plus 5j. So he's heading off in this direction. And every hour that's what he does. -12i plus 5j. So after 1 hour, he starts off here at time 0. At 1 o'clock in the afternoon he's there. 2 o'clock in the afternoon he's there. So that's what's happening. Now the only real formula you need to learn, it's not really a formula, it's more obvious, but the new position of the moving ship is equal to the original position plus the velocity vector and then however many hours have passed. So t lots of the velocity vector. So every hour you do another velocity vector, and then if you add that to your original starting position, that's your new position. It's fairly obvious, but you can think of it as a formula or just think of it as obvious. So for example, if I wanted to make a vector equation telling me where the orange ship is at any given time. So the orange ship, I might actually see if I can, haven't got much room. Orange ship at time t is going to be at its original position, -4i plus 3j, plus t lots of its velocity vector, 4i plus 17j. And the white ship at time t, I might just get rid of these pictures now, hopefully. Hang on. That's a bit better. Okay, so the white ship at time t. White at time t is equal to 4i plus 9j, that's where it started, plus however much time has passed, lots of its velocity vector, which is -12i plus 5j. So that's where they both are at time t. So if I wanted to find out where they were at 2 o'clock, I'd stick in t as 2 and then add it all up. You can write these in terms of their I and j components. If you like, how much I have we got? -4i plus 4ti. And how much j have we got? 3 plus 17tj. And for the white ship, we've got 4 minus 12ti. That's how far left and right. And 9 plus 5tj. That's how far left and right. So you probably got the idea already, even if you didn't from the question, that if this one's going this way and this one's going this way, they might crash. So what happens when ships crash is that they are in the same position. That probably sounds really obvious, but they're in the same position. Now, at the moment, if I line them up like this, for example, the position vector of the orange ship might be 5i plus something maybe, 5i plus 10j, and the position of the white ship is 5i plus 6j. So they've got the same I coordinate, but different j coordinates, and ship E is due east of white ship is east of the orange ship. East? What am I talking about? South. The white ship is south of the orange ship, and the orange ship is north of the white ship. So if two objects are north and south of each other, then their I components will be the same. So this will equal this. Now, what about this situation? Okay, let's make it east. Now the white ship is east of the orange ship and the orange ship is west of the white ship. And in this case, for example, we might have that the orange ship is at 1i and 10j and the white ship is at 3i and 10j. So their I coordinates are different, but their j coordinates are the same. So this 3 plus 17t would equal this, 9 plus 5t. Now if they crash, then they are in the same I position and as well the same j position, and we can use that information to find out what time they're going to crash. So if they're in the same I position, that's when they look like this, so one of them is north and south of the other one, then the I bits will match. So minus 4 plus 4t would equal 4 minus 12t, and that's going to happen when 16t is 8, t is half an hour. So after 30 minutes, they're going to crash. Well, no, they're not necessarily going to crash. After 30 minutes, they're going to be north and south of each other. They're going to have the same I coordinate. Doesn't mean they're going to crash. If I want to check if they're crashing, I need to see if they're also at the same time east-west of each other. So let's find out when they're east-west of each other. That would be when the j coordinates are the same. 3 plus 17t is 9 plus 5t. So 12t equals 6. So again, t is a half. So after 30 minutes, their I coordinates and their j coordinates are the same. That means they're in the same place, and that means they've crashed. Is that what we were trying to do? Show that A and B collide. I have done that. Find the time of the collision. Well, the time of the collision isn't 30 minutes. We started at noon, so the time of the collision would be 12:30. Okay. And the position vector of the collision. Oh, I want to know where the crash site's going to be. Well, the crash site's two ways of thinking about it. The orange ship has gone minus 4i plus 3j. That was its start position. And then it's done half of its velocity vector. Its velocity vector, don't forget, going in that direction, that's what it did in 1 hour, was 4i plus 17j. But it's only done half of that. So the new position is equal to the original position, minus 4i plus 3j, plus the amount of time that's passed, which is a half, of the velocity vector. And that gives us a position vector of minus 2i plus, I think, 23 over 2j. Well, I can check that actually, because in theory, if I'm right, this ship will be in the same place, and the white ship. And the white ship started off its new position after the 30 minutes will equal its original position, 4i plus 9j, plus the time, which is half an hour, half of its velocity vector it will have done, and its velocity vector was minus 12i plus 5j, and that comes out to be minus 2i plus, yes, 23 over 2j. Yeah, that's where they're going to crash. So the crash site is at minus 2i plus 23 over 2j. Just a reminder while we're looking at velocity vectors that if you did want to know the speed of the orange boat and the speed of the white boat, the speed would be the length of the velocity vector, and you would just work that out using Pythagoras. So for example, the orange one, its speed would be 4 squared plus 17 squared square rooted, and the white ship, its speed would be 12 squared plus 5 squared square rooted. Now, sensibly, the orange ship is going to change its course so they don't have a crash. So it's going to start off where it started off before, which is, what was it, minus 4i plus 3j. And it's going along with the velocity vector that it had before, which is 4i plus 17j. And the other ship is, actually he's not doing anything, he's just leaving it all up to the orange ship to sort it out. So he's still going to start off at 4i plus 9j, and he's going to stick to his other velocities, not having any of this getting in the way stuff. He wants the orange one to sort it out. So he's going to do minus 2i plus 5j, and that's what he's doing. So the orange one does this for a quarter of an hour. So he's going in this direction for a quarter of an hour, and then he says, oh, we're going to crash. I've worked it out, so I'm going to change my velocity. And he changes his velocity after a quarter of an hour. He changes it to 16i plus 17j, which is quite almost at 45 degrees really. 16i plus 17j. It's more sort of, actually I didn't draw the other one very well. The other one should be much steeper. 4i plus 17j looks more like that. And what he's going to do is he's going to go more in this direction, which is 16i plus 17j. Okay, now what's going to happen at 12:30? Well, the white ship at 12:30, we know where he's going to be. He's going to be at the old crash site. He's going to be at minus 2i plus 23 over 2j because he hasn't changed anything. What about the orange one? The orange one, well, we've got two original positions to think about. There's his original position, which was here. Then after 15 minutes, he changes direction. So really, this is his original position where he changes direction. So let's work that out first. Orange at 12:15 is the original position, minus 4i plus 3j, plus the time, which is a quarter of the velocity vector 4i plus 17j. So that's where he is at 12:15, and that simplifies down to minus 3i plus 15 over 2j. So that's where he is at 12:15, and that becomes his original position for the next part of the movement, which is another 15 minutes. So orange at 12:30, this is another 15 minutes later, is the original position, which is position at 12:15, plus t, which is quarter of an hour, lots of his new velocity vector, 16i plus 17j, which comes out to be, well, I make it I plus 47 over 4j, which doesn't look very pretty, but that's what I got. Maybe I made a mistake that you can tell me about. So that's where he is. Now what we need to do is the distance between the two, and that's something a bit more tricky to think about. So I'll just clear the board and have a look what's going on. So what have we got? We've got the white ship at the old crash site, which was minus 2i plus 23 over 2j, and we've got the orange ship at his new position, which is I plus 47 over 4j, which is a tiny bit higher, I think, and that's where they are. And what we want to know is the distance between the two. Now the distance between the two is the length of this line, and this line could be described by a vector, and then we could find the length of that vector. Now this is another little formula for you to learn. A to B as a vector is the vector B minus the vector A. Vector B minus the vector A. So it's fairly easy to explain why that is. If I want to get from here to here, it is the same to go down here and then up here. Longer, but the same. This is the vector minus A, if the white ship is A. This is the vector minus A because from here to here is A. So from here to here is minus A, and then from here to here is B. So if we do minus A plus B, or B minus A, then we end up going from there to there. So if I know this position vector and this position vector, I can find this vector, and then I can find the length of that vector. Let's have a go. So white to orange equals orange minus white. Orange position minus the white position, which is I plus 47 over 4j minus 2i plus 23 over 2j, which gives us 3i plus 1/4 j. That's 3i plus 1/4 j. So the distance is the length of this vector. Obviously that's really easy. 3 squared plus 1/4 squared, square rooted is the distance. Can't really be bothered to calculate that, but I'm sure you can do it.